Good afternoon, everyone, and welcome to this month's Research Town Hall. We are going to be joined today by some researchers and colleagues from the Speed School of Engineering and the College of Arts and Sciences. Dr. Klein, would you like to start us off with any leadership updates you may have?
Sure. We have had some fairly good news lately that I wanted to share with you. And most of you, or many of you, may be aware of this already. But in the latest federal budget, as I've said several times publicly, there is an appropriation for a new bioscience building that'll be constructed just south of Eastern Parkway in the green space behind the Speed School and adjacent to the new engineering building. It'll be part of our innovation district. We'll talk a lot more about the innovation district as time goes on, but I think it's going to be an exciting area for faculty as well as students. And overall, we've done well in the federal appropriation in the budgets. There's some other projects that we'll be rolling out in the weeks and months to come. The state budget is kind of up in the air. It's being finalized right now. But the original budget that came from the House side actually had a 7% cut for the University of Louisville. That would affect all aspects of the university, but research certainly would have been affected. Those cuts have now been restored, at least as of 12/02 today. The funding for our base funding, what we call general funds, is back to where it was in the previous biennium. So we think that that's an important contribution of the state to the university and reflects all the hard work that people have been doing to reach out across the state. There's some other things going on. I won't go into them today, and I'll save that for the next town hall. Back to you.
Thanks, John. So our first presenter this morning or this afternoon is Dr. Bikram Bhatia from the School of Speed School. And he's going to be talking to us about his project on reimaging our energy systems and new directions in heat engines, heat pumps, and heat exchangers. So Dr. Bhatia, do you have any slides you would like to share?
Yes, thanks, Lee. Can you see my slides?
Yes, we can.
And can you hear me okay?
Yes.
Okay, great. Thank you. Thanks for that introduction. Hello, everyone. I'm glad to have this opportunity to briefly share some of the highlights, really, of the work that we've been doing in our group here in mechanical engineering at the Conn Center within the Speed School. I joined the University of Louisville in fall 2019. And since then, we've had the opportunity to work with some great students, worked with several collaborators, several of them at the University of Louisville, and also a lot of small businesses primarily, who we often tend to partner with and receive support from different funding agencies, federal agencies, and state ones. Our group's name is the Pyroenergy Research Lab. Pyre, it comes from the word pyre in Greek, that basically stands for fire or heat, basically to indicate that our expertise is in heat transfer, and we look at all kinds of problems related to heat transfer in different areas, but we're for the most part focused on challenges related to energy applications, and that's sort of what I will be focusing on for the time I have today. So just to start off with a big picture, this is a sort of a, a big picture view of our total energy infrastructure. So if you look on the left here, it shows the different sources we get our energy from. It includes solar, nuclear, all the way to petroleum. And if you look at all of these sources, including part of the solar, nuclear, geothermal, natural gas, all of these coal, um, essentially involve the conversion of some fuel into thermal energy or heat. And if you look on the right-hand side, this is basically how we consume a lot of this energy, which also includes HVAC in residential, commercial, and industrial applications for different industrial processes. So on that side as well, you see that you have a lot of this consumption basically being takes the form of heat, right? So, and if you look at the extreme right here, we have rejected energy. So we actually lose 60% of the total energy that we produce, and almost all of that is also in the form of heat. So the basic takeaway from this map is that heat is really at the heart of our energy infrastructure. And if you look at the different components that comprise our energy infrastructure, you see these involve things like heat engines. So these are basically your power plants that either run by coal or other sources, involve conversion of heat into electricity, heat pumps that are the basis for your air conditioning and refrigeration, heat exchanger, which again, you find applications all the way from your laptop to large industrial power plants, and then also energy storage, which again is getting more and more important. So the common thread in most of these applications is that almost all of these energy systems rely on fluids, liquids, gases, and so on. And over the years, that has worked really well for us, but there are some limitations. The efficiency of these fluid-based energy systems has been limiting. Also, it doesn't really allow operation at really high temperatures, which again is linked to the efficiency, and also limits the amount of heat you can store, the reliability of these fluidic systems, and also the leakage problems that you might face, right? So there are a lot of challenges associated with this fluid-based energy infrastructure we have. So in our lab, what we've been really focused on is reimagining these energy systems. And the common theme is trying to replace the fluid-based energy systems with solid materials that can offer higher performance in a lot of cases. They can be much more efficient. They are more reliable. They also can allow operation in zero gravity or in space applications, where fluids become really complicated to deal with, and also you get rid of the problems like leakage. So in the short time we have today, I'm just going to give you a brief overview of a few of the examples that we work in our lab, just to give you a flavor of the kinds of work we do, the expertise we have, and some of the methods that we use. So I'll start off with our work on solid-state heat engines. So heat engines, if you've not heard, is basically the central component of our energy production system. So what it involves is essentially a volume of gas or vapor which you take through a series of pressure and temperature changes across a thermodynamic cycle, which is sort of pictured here on a volume versus pressure diagram. So you go through this thermodynamic cycle, and in the end, which is represented by this curve, area under this curve, you produce some useful work. So in the case of a power plant, that is mechanical work which gets converted into electrical work, and that's the electricity we get in our homes. So the great thing of these heat engines is that they've been perfected over all these years, and their efficiency is really quite good, 50–60% for our typical power plants. And as you go to higher and higher temperatures on the hot side, so basically when you produce heat using that fuel, whether that's natural gas or coal burning, the higher the temperature, the higher the efficiency. So over the years, the efficiency has become quite good. And that's kind of what we're trying to focus on. But we want to get rid of the complex fluid-based power cycle and replace it with solid state materials, something like a material known as pyroelectric. And if you've not heard of it, don't worry. You've definitely seen at least one of these applications. So if you look at the motion sensors in your buildings, the way it works is it has a pyroelectric element in it, and it uh, intercepts the radiation that you give out. All of us do. And that signature gets converted into a temperature change in the material, and that results in an electrical current that gets generated. So we want to use the same idea, except this what we call as a polarization, or the charge within this material is a function of both temperature as well as electric field. So it's very similar to a traditional power cycle, where we take the volume of gas through a series of volume and pressure changes. Here we can change this solid material and take it through a series of temperature and electric field changes to produce useful electricity directly. Without any moving parts, it's just a static solid state material. And what we want to do is basically put heat into this material through radiation, and also reject the heat through radiation. And the reason we want to do that is because we are looking at applications such as wireless powering of drones. So this is something that the Department of Defense, now the Department of War, has been interested in. So the problem that they're facing is that they have all these drones, which typically use a lithium-ion battery, which can run for a certain while. But when you have to charge it, you have to land it again and recharge it, and then take off again. So which is a problem. So what they really want to do is use a high-power laser on the ground that is optically tethered to this drone, and you can basically just in-flight charge the batteries on the drone and essentially fly it for forever if you wanted to. So for an application like this, solar cells turns out work really well because it can match the band gap of the laser. The band gap of the solar cell can match the wavelength of the laser, and the efficiency can be really good. The problem, though, is even that small percentage of inefficiency as you go to higher and higher powers result in large increase in temperature of the solar cells. And if you know something about solar cells, you know that as the solar cells heat up, their efficiency starts to drop. So it doesn't work really well with high power lasers. So if you look at a heat engine, as I just said, as you go to higher and higher power, you basically produce more and more heat. The higher the temperature, the efficiency actually increases. So it makes a lot of sense to have a heat engine. If you can have it in a solid state form, which is what our goal is, you can actually achieve, at least theoretically, really good performance. So that's something that we've been exploring in our lab. We've worked with these solid state heat engines, and we worked with this radiatively driven thermal switches, which can basically intercept the laser and essentially produce heating and cooling of the solid material, again, without much moving parts. But you can produce useful electricity directly using these thermodynamic cycle, like I talked about. And in our proof of concept results, we've shown that with this thermal switching, you can actually improve the overall efficiency as opposed to when you don't have this thermal switching. So this is actually quite powerful, because what I'm saying here is that with the same amount of energy coming in, even though I have some loss because of the optical elements that I'm introducing, I can actually produce more work out than if I don't have this radiative switching, which is our sort of our innovation and contribution. And if you scale this up to a real world system, which is represented by this endo-reversible heat engine, which sort of turns out models our existing power plants very well, you can see that these efficiency improvements can be really, really substantial, and can result in billions of dollars of savings. So this is some work that we did in collaboration with Professor Sergio Mendes in the physics department. And so with this, I will move to my next example, which is focused on heat pumps. So heat pumps, you might have heard, has been a big priority of the Department of Energy. to transition us from furnaces for air conditioning and refrigeration applications towards heat pumps. And the reason is these heat pumps can be really efficient. Typically, they use refrigerants, which have some problem, the fact that they have very high global warming potential. So people have been exploring other solid materials to generate this heating and cooling. You can use the different solid materials when you apply a magnetic field, or you can stretch some materials and produce heating and cooling that way. But again, all of these existing solid state based methods have problems associated with cost, scaling, and their efficiency has just not been very good. We've been looking at a different kind of solid state caloric effect is what it's called, where essentially we take a material and we apply compressive pressure or compressive and expansive pressure, so hydrostatic pressure. And the idea is actually very simple. If you take a piece of rubber, for example, when you apply pressure to it, you notice that it heats up. And then when you release that pressure, it actually cools down. So that's essentially what is known as a barocaloric effect. And we've tested a bunch of materials in our lab. We have this custom setup. We apply a pressure, it heats up, and then we release this pressure and it cools down, comes to room temperature. And then when we release this pressure, actually, it can go to really low temperature. So with this sort of representative material that I'm showing here, you see that when we're operating at room temperature, we can get to temperatures as low as 0 degrees Celsius, which means we can theoretically at least make ice by just compressing and allowing the material to relax. We characterize the performance of this heat pumps using two main metrics. Is basically how much power I'm getting from this heat pump, so what size your heat pump needs to be, and the COP, which is kind of like the efficiency, but not exactly. So it's basically how much useful heating, let's say, you're getting out, divided by how much mechanical work you're putting in. So that's the definition of COP. These COPs, unlike efficiency, can actually be greater than 100%. In fact, it is almost always greater than 100%, which is why the DOE has been really intent on everyone moving towards our household, from moving away from our furnaces in the house to heat pumps, because you can actually produce theoretically at least 300-400% efficiency, if that makes sense. We're not violating any laws of thermodynamics. It's just that the way we operate a heat pump is different from a furnace, and you can have much more heat generated or cooling generated relative to the amount of work that you put in. So the typical COP of a heat pump at your home would be something like 3 or 4. And so we've done a lot of modeling of these systems, and we've also built experimental setups to actually have a heat pump prototype with some help from the Additive Manufacturing Institute we have on campus to 3D print this custom heat pump core. And we've operated this heat pump like a regular heat pump, and we measured, so this is the first experimentally measured COP of a barocaloric heat pump. And we see that even with a common material, here we were using natural rubber. This is not the best material out there. But with this low cost, readily available material, we could get COPs of 3 or 4 in this case, more than 4, which already is very competitive with the existing state-of-the-art heat pumps. And we think with newer materials and better designs, you can get to much higher, even higher, significantly higher efficiency. So we are very excited about this work on heat pumps. And with the last example I want to give is move towards some work that we've done on heat exchangers. So here we're looking at solar powered application. So this is if you people typically associate solar power with solar cells, but this is the other kind of solar power where you essentially focus the heat of the sunlight with many mirrors, typically on the top of a tower. You heat up a material really high at high temperatures, and then use that to drive a quote unquote traditional power cycle or a heat engine. So with a lot of work over the last few decades, the DOE established that they want to look at mostly solid materials, because just the fact that they can go to really high temperatures, They don't have problems like corrosion and such. And the most important thing is you can actually store this heat in the form of these solid particles at high temperature quite easily. It's very easy to store heat. It's low cost. And whenever you need that energy, you just run it through a heat exchanger, uh, power or raise the temperature of a secondary fluid that can run your turbine and produce electricity. The problem though is the heat exchanger, because getting the heat out from solid particles into the secondary fluid becomes complicated. And that's the problem that we are focused on. You can have different kinds of heat exchanger designs. You can have a heat exchanger design where you have these particles, hot particles falling down through gravity, raising the temperature of this fluid, or which generally tends to have relatively low heat transfer performance. Or you can have this fluidized kind of system where you basically inject compressed air, you agitate this hot sand essentially, and that improves the overall heat transfer performance. But then there are some challenges with the operation. So we've looked at both of those and try to basically improve the performance of these heat exchangers. So we have this custom experimental setup in the lab where we use silica alumina sand, and we looked at all these different kinds of heat exchanger coupons, and we specifically studied the uh, effect of the heat transfer from this solid particle to this tube wall, which is turns out the bottleneck. And by optimizing these geometries, really improved the performance of the heat transfer. Turns out the airfoil geometry, which is kind of like the geometry of the airplane, turns out is really the best geometry, which again wasn't really investigated before, and something that we came up through our investigations. And then we further improved our heat transfer performance by looking at the fluidized system. Again, we have a prototype for this in our lab. We can do high-speed imaging and really track individual particles to really figure out how the heat is flowing from these sand particles into this tube wall coupon. And this turns out a really complicated fluid and heat transfer problem. And so we've utilized a machine learning approach to really track all these particles. And just like a lot of folks are doing in the Silicon Valley, where they're trying to code themselves out of a coding job, we are trying to essentially develop this machine learning platform so that we don't have to run heat transfer experiments, which turns out are very expensive and complicated, to essentially give us the heat transfer performance without running any heat transfer experiments. So here I'm showing the heat transfer coefficient, which is a measure of how good the heat transfer is from these particles into the tube wall. And we find some really interesting insights that tell us how we can improve the overall fluidized bed heat exchanger for example, solar thermal applications. And so with that, I would end here and just say that hopefully these examples give you a flavor of the kind of problems we work on and our expertise. And if you have any heat transfer related problems you think we can help with, please reach out. My email is right here on the slide.
Thank you very much. Very interesting. Does anyone in the audience have any questions? No? Bikram, can you stop sharing?
Sure.
Thank you. So I did just drop into the chat an announcement regarding the new Genesis mission, Transforming Science and Energy with AI. This is a solicitation that is seeking applications for both at phase 1 and phase 2, and it's around advanced manufacturing, biotechnology, critical materials, and nuclear fission or fusion, and quantum information science and microelectronics, discovery science, and energy. So as you can see, if you open up the solicitation, there are over 99 different focus areas. And so I wanted to bring this to your attention since it part of Bikram's was talking about energy. There may be some people on here that would be interested in this solicitation. We are calling for internal applications, which are very short and sweet, and we will turn around very quickly who may move forward. I mean, it's limited in the amount of people that, only one can go out per focus area, but we just want to make sure by putting it in limited subs database that we're not trying to submit, two faculty be interested in submitting to one focus area. We want to make sure that no one is excluded. So if anyone has any questions about that, or would like to learn more, feel free to reach out to me or Cecilia Pareto. All right, our next speaker is Dr. Hui Wang, and Dr. Wang is going to be talking about engineering materials for safe and sustainable energy storage. Dr. Wang, are you on the call? All right. Maybe they are having difficulty logging in or something. So we'll move to the other presenter. The other presenter today is Farshid Ramezanipour. I hope I pronounced that right. If not, my deepest apologies. The topic that Farshid is going to be talking about is designing electrocatalytic materials for sustainable hydrogen production. And so, Farshid, I'll turn it over to you.
Thank you. Let me go ahead and share. Okay, hopefully you can see my screen now.
Yes, we can see it and we can hear you.
Fantastic. All right. It's great to be here. Thank you for the opportunity to tell you about some of the work we've been doing on hydrogen production. Specifically, this is an attempt on developing materials for a more sustainable way of generating hydrogen. And what I'm going to do today is sort of just giving you an overview of the work we do without going into too much detail. And hopefully we can establish some collaborations as well. You mentioned the Genesis FOA, which is out. This is actually, thank you for bringing that up. I have been thinking about the proposal on that. So I am looking for team members. That would be great. If I can join other teams, I can bring my ideas, and other people have ideas, would be great. All right. So before I start, let me just acknowledge the people who actually do the lab work in the lab. And that's basically a large number of PhD students, postdoctoral researchers, some undergraduate researchers as well. And specifically, I would like to acknowledge the work of our PhD students. Without them and without their contribution, I think it would be very difficult to push the research mission of our university. And I want to just probably highlight the other contributions that they make, and that is many of these PhD students also work as GTA. And, as GTA in chemistry, at least, some of these students teach up to 6 labs per semester per year. Which that's how we can run undergraduate labs for relatively low cost. So their contribution is not limited to research. They also help us with the undergraduate education, just something to highlight here. And again, to emphasize the contribution of these PhD students and the research impact that they have, I'm going to take about 2 minutes just to talk about that and the effect that they have on sort of the reputation of the university. If you look at the Times, the higher education ranking criteria, you'll see that this is shown here on the left, but basically the summary of it is that 70% of the criteria as far as Times higher education goes is research related. And PhD students are essential to our ability to actually be able to do that. And of that 70%, 7.5% is about research funding, and the major share is reputation from annual surveys, 18%. And then, of course, 15% from citation. Why am I bringing this up? Because I think there is another side to this story, which is I personally, as an advisor, I feel responsible for making sure that my PhD students have the best chance when they graduate. And I can do that by giving them as strong of a CV, as strong of a resume as possible, by giving them as many publications as possible. So I think there is this side of the story of research that I believe needs to get more attention, and that's the importance of publications to the success of our PhD students and also to the reputation of our university. Here is the 2026 ranking from Times Higher Education. University of Kentucky is ranked among the top 500. University of Louisville did not receive ranking. Now, if you delve deeper and go read the documents for Times Higher Education ranking method, they actually say that the universities would be excluded if the number of publications doesn't reach a certain level and if the distribution among different subject areas is not appropriate. So again, these are things that I think are important to pay attention to, the fact that publications matter, need to be incentivized, and it's important to incentivize research across all units in the university. Even the US News and World Ranking, basically that's a ranking that puts even less emphasis on research, but it's still the biggest share of ranking pie there is peer assessment, 20%, which again goes back to reputation. And in terms of research criteria, again, even US News puts the most important component as publication. This is the UK publication, 20,000 something. UofL publication, about half of that. The long-term impact, I think, is important because I understand we typically have budget problems. That's something that keeps coming up for different reasons each sort of year for a different reason. But I think it's important to keep in mind the long-term plan and the impact that research has on the university reputation and what it can do for undergraduate education, experiential learning that we can bring to undergraduate students. Of course, parents, students want to choose universities with more prestigious designations. And of course, I mentioned the impact of our PhD researchers on also our undergraduate education. So what I'm hoping we can do, again, just as researchers, I don't think I should just do my research and not think about the bigger picture. I think this is something that we hopefully will do. And hopefully there will be platforms for us to brainstorm about how we can enhance research and undergraduate education simultaneously. There are things that can be done, small incentives. There are practical initiatives that have low or no cost, actually, things that can be done practically. I have had some communications with Dr. Klein about that. I have some ideas about, things that could be done, scaffolding research across curriculum. We could actually start from year one and, many other things. So hopefully as researchers, we also start thinking about, not just our own research, also about how we can contribute to the university as a whole in terms of research profile. All right, so let me move on to the work that we do. We work on designing materials with specific atomic arrangements for energy storage and conversion. And this is important because every functional property can be modified by controlling the structure, and that's the arrangement of atoms. And the type of materials that we work on are these sort of network materials where you have the atomic network. You don't have individual molecules, but a network of atoms all connected to each other, forming these three-dimensional systems, which are really essential to many applications, such as lithium-ion batteries. So this family of materials that we explore actually are the basis of the lithium-ion batteries that were developed, and Stan Goodenough, Stan Willingham, John Goodenough, Akira Yoshino together, they actually got the Nobel Prize for using these materials in order to develop lithium-ion batteries. Here's a photo of Stan Willingham at the SciLog conference. I had the pleasure of working with him for 3 years, and I'm a SILOC fellow in advanced energy storage. So in SILOC conferences for 3 years in a row, we used to have brainstorming sessions, and of course, Stan Whittingham was one of the leads in those brainstorming sessions. So it was really a pleasure to work with him. So that's the family of materials we work on, but lithium-ion batteries are not the only area where we are interested in. So here are some of the materials that we have developed in our lab, and here are some applications that we've done. Again, I obviously won't have time to go through all of the applications, but we've used these materials for magnetic properties. We have actually shown that you could switch magnetic orientation by changing temperature in these materials, get magnetic ordering of one type at one temperature and another type at a different temperature. We have used these materials for electrocatalysis, specifically for hydrogen production. And this is a project that I still claim has developed at least 2 of the best ever electrocatalysts in this field. And I'll talk about that in a minute. We've used these materials for charge transport, which of course is essential for energy storage and conversion, ionic conductivity, specifically for lithium-ion conductivity for batteries. We've used them for gas sensing, again, such as carbon monoxide sensing. If you want to basically make sure that the carbon monoxide level doesn't reach a certain level, you can actually use these materials. We've shown that property. They've also used these as pseudo-capacitive energy storage materials. And that's an interesting area because it's an intermediate between battery energy storage and capacitor energy storage. You're trying to get both high energy density and high power density. And we've been able to show that these materials actually can do that for us, store energy, give us high energy and power density at the same time. And we also have some new projects of using these materials for solar cell applications. But our currently active projects, again, the ones that we are focusing on the most are a few. One of them is this one, basically designing vacancy ordered materials, the material development aspect specifically, and that's funded by NSF Career Award and also an NSF grant that was awarded just a few months ago, about 6 months ago or so. We also have another focus right now, hydrogen production. As I said, this is really important, developing materials for hydrogen production from water splitting. This is funded by a project, by a grant from Research Foundation Flanders in Belgium. So this was actually in a collaboration with a European colleague. And we are working now sort of this cross-Atlantic collaboration, which has been really interesting and helpful, and also sort of establishing those networks between the UofL and European institutions. We also have some projects on pseudo-capacitive energy storage, as I mentioned. We have a pending proposal with DOE right now on this. And another project also on another way of hydrogen production. This is using chemical looping reforming. So my second project, as I mentioned, is hydrogen production from water splitting. This one basically uses a more traditional method, but tries to actually bring down the carbon footprint as much as possible. So this is funded by the American Chemical Society Petroleum Research Fund. And finally, the fifth main focus that we have right now is trying to develop divalent ion conductivity for solid state oxides, and that's for next generation of batteries, hopefully batteries that can give us more of an energy density, because now we are using divalent ions. So that's the overview, and I'll try to maybe go through at least 1 or 2 of these projects in the next 5 to 7 minutes.
Farshid, this is Lee.
Yes.
Looking at the clock, we were able to get in touch with Dr. Wang, so we wanted to make sure we have time for her to speak as well. So you've got about a couple of minutes, and so we wanted to make sure you know that, the time constraint you've got.
Of course. Sure. Yes, I'll try to wrap it up in about 2 minutes. Does that sound good?
Okay, that sounds good.
Thank you. All right, so designing materials for hydrogen production. Let me just point out what we are doing here. We are taking electricity from renewable sources. We are splitting water into hydrogen and oxygen. And of course, hydrogen is essential to our way of life, because otherwise we wouldn't be able to make ammonia, which is essential to fertilizers for agriculture. So feeding the world really needs hydrogen. Another thing is that our hydrogen is a clean fuel, so we could actually use that for running vehicles. Right now, there are a lot of buses in different states that actually run on hydrogen, and this is actually expanding more and more now. So that's the idea. There are two half reactions for this process, and one of them is the bottleneck. There are materials that facilitate this project, this process as catalysts. Right now, the main ones are noble metal catalysts, noble metal materials. We want to do that, and this is actually a large scale production system which already exists. We want to do that using our materials that are not based on noble metal. They are earth abundant. And it started from this project. This is this paper in Science that introduced the material, non-noble metal material, being able to do that process for us, especially this anodic process. This is sort of the bottleneck. And we sort of decided to expand on this. We realized there are ways that we can actually improve this. So we started developing materials based on perovskite oxides, specifically by incorporating vacancy in them, and developing materials like this. These are some of the compounds we've made. And here's an example of the analysis that we do: neutron diffraction, X-ray photoelectron spectroscopy, other kinds of analysis. But for today, basically, the main thing is that I want to just focus on this one thing. We can do things so that we can lower the electricity needed. So this plot needs to shift to the left. That's basically the main thing. Here are two materials of examples of our things that we made. The change in the structure changed the electronic structure and led to improvement in electrocatalytic activity, splitting water significantly better when we have ordering of oxygen vacancies. This was on the front cover of ACS Applied Energy Materials. We have done projects on trying to also nanosize our materials. That has led to really advanced electrocatalysis also for water splitting. This was on the front cover of ACS Applied Nanomaterials recently. We've developed materials also that have shown local structural ordering, again, without going into too much details. This was another work we should feature on the front cover of ACS Sustainable Chemistry and Engineering. And here is the crown jewel, I would say. This material is one of the best ever catalysts in this field. We also have a patent on this. This was featured on the front cover of ACS Catalysis. I have a lot of hopes for this material to be commercialized. And here is an actual video of our materials, how they're splitting water into hydrogen and oxygen. The bubbles you're seeing are hydrogen and oxygen gases that are basically generated from water. So we've expanded on this quite a bit in different sort of areas. Hopefully, I've been able to convince you that we can develop materials for sustainable hydrogen production, and we can do that by changing the structure. So controlling the atomic arrangement, giving us the opportunity to develop these materials for better hydrogen production. I won't talk about the lithium-ion conductivity aspect and the batteries. I just want to acknowledge the funding agencies, also the collaborators from different universities and institutions. I'm happy to answer any questions. It's 12:43 in the next 2 minutes. Thank you.
Thank you, Farshid. Does anyone have any questions? Thank you for talking rapidly there. So Dr. Hui Wang is with us, so I'm going to let her share her screen. We can see your PowerPoint, but it's not in presentation mode.
Hello, can you hear me?
We can hear you.
Okay,
there you
perfect. Go. Okay, good. Yep. Okay. Good afternoon, everyone. So I apologize, kind of like it has some of the connection issues, and then yep. Okay. Actually, it's great like to talk after Farshid, because he mentioned about like the lithium-ion batteries and also kind of like the battery materials. My talk actually that is just mostly it's just for electrochemical energy storage, specifically for the beyond lithium-ion batteries. So here this is the title for my today's presentation, and also before I go to the details, I wanted to okay, I'll briefly to discuss, introduce about the project or the research things that in my group at the UofL. my group as see that the solid energy groups that I'm like here to work on this 4 like different areas. I see that it's on the solid state ion conductors, and we focus about the synthesis of materials. And then the other one is like on the solid state batteries, focus about the interface engineer to build about like the stable interface. And also collaborate with about the Dr. Yasik from the Center. We also work on the black phosphorus nanoribbons, and we use electrochemical approaches to produce the materials. And also, I also have the collaborations on the carbon electrode for the perovskite solar cells. This is kind of like a collaboration with Dr. Ted in the Center, and also with another colleague from the Vista State University. Okay, so as I say that back to today, I'm focused about like the energy storage enable kind of like the system of future. So as we see that for the renewable energies, the most as no matter for wind or solar, kind of like our biggest issues is kind of like how stable that is, right? That is to address about that issues, that's kind of like the energy storage that is the best solution. So that's kind of like I see that the energy storage that will be not only can like to the produce for the grid like the electricity, and also for the transportation, and also even for the data centers to build up the energy storage solutions. And for sure, as you aware, it's kind of like the lithium-ion batteries, right? So lithium-ion batteries was I can like go to a market in the almost in the last 30 years, dominate the market. But however, as I see that when that goes from the cell phone, laptops, and go to electric vehicles, safety concerns, that is a big one. So then that is kind of like we have the big challenges is like how can we address about like the flammabilities of the in the lithium-ion batteries, but meanwhile also keep about the energy density. So that is kind of like we will see that to develop for the next generation batteries. So here is kind of like it's called solid state lithium or solid state sodium batteries. So the structures is similar. You see with the lithium-ion batteries have anode cathode, but the difference with the traditional about the liquid electrolyte with the flammable or the organic liquid, we do use the solid ion conductors to replace the liquid electrolyte, and then still can make the shuttle between for the lithium ions. But if it's a solid state sodium batteries, we will have the sodium ions that are back and forth as between electrode. Actually, for solid state batteries, I see that not only increase about the safety, and also we can use about the lithium metal or sodium metal as the anode, then can increase about the high energy density. In the past of the 10 years, this is kind of like a review article that we, I write with the other 3 colleagues, and then to track about in the past, about like 10 or 12 years about what's the trend for the solid state batteries. We will see that in the academic side, that is the literature, it's kind of like rise quickly. And besides that, you also may can like look at about like the companies, they all talk more about the solid state batteries, especially for the solid power and then quantum escape, which can like focus is kind of like for the solid electrolyte materials for the kind of like solid state batteries. So the research in my group actually, or at least in today's presentations, I mostly will focus about the solid electrolyte, which as you see that for the anode and cathode, as you see, solid electrolyte is the biggest change between the conventional lithium-ion batteries with the solid state lithium batteries. There are a lot of the expectations for the new materials. For example, we want that is have fast ion transport, and we also want to like have the interface stability, so that's kind of like a can stable interface, and also can have the dendrite suppression. And also meanwhile, we also hope that it can be easy process, and also can have the low cost materials. And so that's kind of like have a lot of expectations for this. So to meet this kind of like the expectations, and then we do also consider about like there are different types of materials for choice. So we have inorganic, we also have polymer, or we also have the composite electrolyte, which can like will be consistent of the polymer and the inorganic. So, but that ways kind of like will be can combine kind of like the advantage of the high ion conductivity from the inorganic, but also can take about like the flexibility and the interface of the polymer electrolyte. So that's kind of like as you see that there has been a lot of the studies about the kind of like the solid composite electrolyte. This is also kind of like a review article that we write about kind of like different type of the inorganic, like the sulfide, the perovskite type, and the garnet type, and for to make about the solid composite electrolyte. Okay, so for today's research, the presentations, I mostly focus about the synthesis. So we're trying to solve about the issues of the solid electrolyte from the synthesis perspectives. So I will be, quickly go through about the different three different perspectives, and then to share about like our research start from the polymer rich one, and then go to about the composite, the ceramic rich, and also we share also a little bit about the pure inorganic solid electrolyte. So all those kind of like three are focused about the solid electrolyte materials. So for the polymer rich one, actually that is kind of like our first design is kind of like we want trying to make about the ultra thin and also flexible the solid electrolyte. So especially think about like for some of the wearable devices, and also in some applications that require the solid electrolyte is folded. So then that we can like use this design to start about to use the polymer rich composite. So our design is kind of like we use about the sodium the inorganic, the sulfide inorganic, and then to mix all in, or can like distribute it in the polymer based solid electrolyte. So we have the sodium PF6 with PVDF. So this is kind of like a matrix, and then this is like the way prepared like those kind of like the semi-transparent. Actually, before we bring about the inorganic or the sulfide, it is transparent. And after we bring the sulfide, then the color goes to kind of like a little bit brown. And also this color is also depends on how thick it is. So this is kind of like also we have a study to look at about our goal is trying to get it thinner, and then to have about the solid electrolyte. The things like if you look at about the solid state batteries, actually you will realize about the solid electrolyte part will be kind of like take the most of the thickness. And then we can like during our studies we do observe about like the thickness, it's kind of like does influence about the electrochemical performance. So we compare about these three different thickness from the 20 micrometers go to about 40, and then go to 65, and then we cycle that in the batteries, and we assemble in the like the battery, and then to compare about here how does the thickness influence. So our conclusion get that is kind of like that it will be the thinnerest one give us the best the kind of like the performance. And then this one was also published kind of like in the SS applied energy materials. And actually for the thin ones, we also to look at is in the titanium disulfide one, and then which can have like get about like the rate can achieve about the higher rate performance. And also we demonstrate kind of like the stability up to 300 the cycles, and then to use about the sodium metal as the anode. And also can like we choose about not only for the least solid sodium one, we also actually the lithium solid state lithium batteries we also use the kind of like the design for this one. It's kind of like this is just like for the we use aguardite and then PVDF and then lithium PF6 salt, and then to make this is flexible composite. As you see that this one we can this thickness is kind of like can go to about like 150. We feel that is already can like that is highly flexible. We can also control that is further go to about below 100 or below about 50. So that's kind of like for the solid state lithium ones. And then we also assemble that in the lithium use the PFC, the lithium iron phosphate, and also with the lithium titanium oxide as the kind of like the anode, and then to make the full batteries. And also for this composite, we even further go to about the small puncture cell. That's kind of like to demonstrate that it can light on the LED light. And then the amazing thing for this kind of like the kind of like the composite solid is kind of like no matter when you folder that or you even cut it, and then the light is still keep on. So that is kind of like increase about the safety of the kind of like the solid state batteries with composite solid electrolyte. So then besides that one, we can like from the polymer rich, that means about the polymer one is already kind of like about 80% in the composite electrolyte. Then we do the next step is like whether we can further increase about the inorganic part to make it, because our understanding is like if you increase more amount of ceramic, then that should be more safe. So then that's kind of like we bring that is design go to about the ceramic rich. So this one we designed to use the sodium antimony sulfide to make that as a self template, and then to embed about the PPP. This is kind of like a phase change polymer. So that was some like come from our previously paper published at 2021. We demonstrate this kind of like the polymer. This like it can be at the 60 degree. It is kind of like it's kind of like a flow, and but however, if that is goes to the room temperature, it will go to the solid state. Then that is we use this one and then to make the palette. And if you look at the this is the top of surface. And amazing thing like for this one, this is kind of like after do the 3D template one, then you can do observe a lot of the pores for in the palette. And then this is kind of like before in the filtration of the polymer. Then this is after that. So then kind of like then we prepare this the kind of like the materials and then assemble in the this is kind of like symmetric cell we study, and then to look at that is with the 3D dimensional one and with the PPP the polymer enriched, then that's kind of like make the interface toward to the sodium metal is dramatically increased. And so that's kind of like to show about this kind of like the ceramic as the main part, and then the polymer on the interface that can like stabilize interface. And we also can.
Wei, can I just give you a little idea of where we are on time? We've got about 4 minutes left, so I just wanted you to be aware.
Sure, give me, okay, I will wrap up quickly.
Okay.
Yes. Okay, so here it's like, it just, again, it's like we test that performance in the, full batteries, and then to, again, like to look at about electrochemical cycling. So for the inorganic here, it just lists about different type of the inorganic materials people are interested. So for us, we focus about like the sulfide. So the unique thing in our group is kind of like we develop about to use wet chemical synthesis to synthesize aguridite one, and then we can can tune about different compositions and control their pure high phase purity and also the crystalline. So this kind of like just some characterizations. And for this one, we work with the IP office, and then we have kind of like 5 patents on the materials and also the interface design. And also here, it's just like we also are the first one to demonstrate about the fluorine doping can introduce to the aguridite, and which can increase not only increase by conductivity, but also increase the interface stability. Okay, then that's kind of, I think that I finished that in 2 minutes. So then this is like a quick summary, is like so this part like I introduced about user synthesis, and then to control about the structure, and then further to influence about the batteries, the performance. And we introduce about like from the polymer rich, from the composite, and then pure like inorganic solid electrolyte to address the challenges in the solid state battery. But my last one is very important, kind of like to acknowledge about the funding support, and also acknowledge about the collaborators. And I also thanks everyone here today, and to also we look about like calibrations. We feel that it's like we work about like the synthesis and also new chemistry discovery, and also we can also do the materials device, but we also do want like about the applications, as we see that in some different devices, like for example the medical devices, robotics, and also wearable devices, or go to the grid storage. We would open, to talk with people who are interested or need, want to know about energy storage, to use for that. So yeah, thank you, everyone. I think that I'm keeping on time.
You did. Thank you very much. I want to thank all of today's presenters. And if anyone has any questions for Dr. Wei, I'm sure she would be happy to speak with you one-on-one, but because it looks like we're right on time here. Next month, I put into the chat, we are going to meet on April 23rd, and we're going to feature Jai-Ping Wang and Rebecca Redmond, who will be presenting on clinical research. And so we'll see you next month. Thank you, everyone.